We will discuss the principles of MIMO technique, what MIMO techniques, what MIMO orders are used in the 3G and before that and after that in 4G and 5G. Then we will discuss the detail of the massive MIMO, single user MIMO and multi-user MIMO, and what are the functionality used in the NR FDD mode and NR TDD mode. After that, we will discuss the beamforming basics and types of beamforming like analog beamforming, digital beamforming, and hybrid beamforming. And then beamforming procedure, how the beamforming happens in the radio environment in our 5G. Then initial access procedure in 5G and scenario-based broadcast beam applications in the 5G. That's all. So we start first from the wireless basic. In order to successfully decode the data, whenever the transmitter transmit the data and receiver receive the data, there should be a minimum signal to noise ratio. Minimum signal to noise ratio to decode that data. And if higher data rate is required, there should be requirement of higher SNR. And second one concept is the signal strength. Signal strength is decreases with the increase in the range of wireless environment. If you move away from the base station and signal strength is deteriorated. The principles of MIMO techniques actually in this slide. So the SISO, no, single input and single output. Multiple MISO means multiple input, single output. And single input, multiple output. Actually, previously in 2G and 3G, we are using multiple antenna in case of diversity purpose. Na? Reception 2 antenna is used for the one is the receive and second one is the diversity receive. Multiple antenna techniques we use in the 2G and 3G in the case of diversity reception. But in the 4G, from the start of 4G, we are using the higher order MIMO, transmission plus reception both, whether it is a diversity gain or array gain or multiplexing gain. We will discuss in detail all of these, and interference rejection gain. So can anyone tell me what are the order of MIMO that is used by 3GPP first in 3G? What are the order of MIMO that is used in 3G first time? In which release actually? Actually, 3GPP release 7, the 3GPP release 7 first specified, and that is the 2x2 MIMO in the downlink. 2x2 MIMO in the downlink, and no MIMO in the uplink, only in the downlink. That means in the 3G network, it is a WCDMA based technology, where all your data transmitted and received on the same frequency on the same time. All users are transmitting their data in the same frequency and same time domain. That's why the 3G is the interference limited network. We cannot move 2x2 MIMO or more MIMO from 3GP release 7 because MIMO requires the noise-free environment, or we can say interference-free environment. If we want to use the MIMO, that means we have to interference-free environment to transmit the parallel transmission of the data in the parallel channel. So OFDM is the techniques from WCDMA to OFDM. OFDM is a technique where we use in the LT that gives the interference-free environment at the radio side. Why? Because all the users are transmitting in the different frequency and time domain resources. That is known as the resource block. 4G as well as 5G, we known as the resource block, where users transmit their data in frequency and time domain. All are having the different frequency and time domain resources. That's why the intra-cell interference, intra-cell interference is theoretically nil, means zero. That's why it's more suitable to, to transmit higher order MIMO in the case of 4G and 5G. Right, and OFDM technology is the also is one of the case that enables the 4G and 5G for higher order MIMO or massive MIMO, because our previous legacy network 3G and 2G are a serial data transmission on a single carrier. But in OFDM techniques, we are transmitting in the multi-carrier mode. Our data is transmitted into multiple sub-carriers. That's why it is more suitable to implement the higher order MIMO and massive MIMO. Now, what are the functions? New radio frequency division duplex and new radio time division duplex. As already all of you know, the our frequency band that is used in the 5G, that is the FR1 and FR2, frequency range 1 and frequency range 2. The sub 3 gigahertz band actually that is used by our legacy network 4G, 3G, 2G, right, is supported both FDD and TDD. In 5G, that is supported both transmission mode, FDD as well as TDD. But in 5G, additional band that is added in the 5G, that is the C band in FR1 and FR2 millimeter wave bands, both are supported only time division duplex mode. Why they implemented time division duplex mode? We will discuss for massive MIMO, and one other case is also there because our 2G era only they are supporting FDD transmission mode. Why? Because our traffic, our voice traffic is 50% time in uplink and 50% time in the downlink. That means we are listening 50% time we are listening and 50% time we are speaking. That's why the traffic balance is there in uplink and downlink in case of voice traffic. But now our traffic scenario is changing. Our all the traffics are now a data centric, right? So there is a flexibility is required. That flexibility, the TDD mode, frequency band TDD mode, it gives the flexibility. Whatever time number of time slot you want to give for downlink, and what number of, if you want to allocate less number of time slot in uplink, you can allocate like that. Much flexibility for uplink and downlinks provides in the TDD model. Four functions name written here: PMI based weights. PMI means pre-coding matrix indication base. Actually, there are two main reference signals, that is the CSIRS and sounding reference signals. CSIRS reference signals is used in the downlink direction for estimating the channels, right? And sounding reference signals is used the estimation of channels in the uplink. So these are the two method actually, the functions PMI based weight and SRS based weight. We will discuss in detail how that these two methods are very important to assigning the pre-coding matrix and beamforming. They are deciding factor for the beamforming. Okay, so PMI based weights only supported in both NR FDD and NR TDD, and sounding reference signal based weights supported only by the TDD mode. And other two methods, that is the single user MIMO and multi-user MIMO. Single user MIMO is supported both new radio FDD mode and new radio TDD mode, but the multi-user MIMO is only supported in the new radio TDD mode. New radio TDD mode. That's why we are called massive MIMO is used in the scenario of multi-user MIMO, not it is a single user MIMO. Now comes on the massive MIMO, starts from the MIMO, then comes on the massive MIMO, right? And massive MIMO suitable for the TDD transmission mode, and it is also specified by 3GPP. That is the only the TDD mode. The massive MIMO works in the TDD mode. Why? Because in the downlink direction, in the theoretical concept, we are saying that the number of antenna is larger than the number of users. Number of antenna is larger than the number of users. If we assigned pilot channels, or we can say reference signals is used in the pilot channel, we assign the pilot channels of each antenna. If we assign the pilot channels of each antenna at the base station, then the bandwidth is consumed. A large number of bandwidth is consumed for allocating the pilot channels to estimate the channel only, estimate the wireless channel, or we can say propagation channels. So for shortening the, or you can say reducing the overhead of pilot channels, they are using the uplink. Uplink TDD mode. In the TDD mode, they are using the same frequency, but the time slot for uplink and downlink is different. In the case of massive MIMO, TDD used because we are only the estimating the channel in the uplink direction by transmitting the SRS, sounding reference signals. And the same channel estimation can be used for downlink also. We only check the estimation for uplink, but same uplink channel estimation can be used in the downlink. That concept is known as the channel reciprocity. Channel reciprocity. That concept used in the massive MIMO, and massive MIMO always used in the time division duplex mode. This slide shows the massive MIMO in the sub 7 GHz, or we can say FR1 and FR2. What are the 3GPP specify for FR1? That is the 64 ports antenna, maximum 64 cross 64 MIMO is specified, and for millimeter wave, you can see currently the 512 ports for millimeter wave is there. 32, 64, 128, and 3GPP actually, if your antenna order is more than 16 cross 16, it term as a massive MIMO. It term as a massive MIMO, 16 cross 16 or 32 cross 32 or 64 cross 64 or 128 cross 128. Right, 256 and 512. These are the antenna ports configuration for FR1 and FR2. Currently, that is used worldwide. This one is the massive MIMO concept that is used as a multi-user MIMO, but here to differentiate the single user MIMO and multi-user MIMO, you can see here the single user MIMO means all the antenna ports are transmitting their signals to a single user, towards the single users. And 4G as well as 5G, maximum in uplink direction, only 4 cross 4 layer is there. 4 layers only is there. Why? Because 4 layers means your UV side, all the antenna are very close, because all the antenna are installed in the very small area. That's why all the antenna is very close. That's why the wireless channels, wireless propagation channels paths are highly correlated. That's why more than 4 cross 4 or 8 cross 8 is not feasible in that case. In the uplink side, there is a maximum 4 cross 4, but in the downlink side, that is the maximum it is 8 cross 8 single user MIMO is feasible, because the orthogonality between the paths or between the propagation channel is not achieved, or you can say very difficult to achieve the orthogonality between the different propagation channels. So if your propagation channel is not orthogonal, highly correlated, that means your data throughput will be less. But in the right hand direction, you can see here all the different layers or the different 4 layers are transmitted to 4 different users. That is spatially separated. That's why it can be orthogonality can be achieved in that case. Because users are or antenna is not located at the one UE. They are now separated in this space. We will discuss the detail of single user MIMO and multi-user MIMO in uplink as well as in downlink. This one is the downlink single user MIMO. What 3GPP specified. The functions uses the multi-antenna technology to enable the downlink multi-layer data transmission for a single UE. Right? Single user MIMO means all the layers that is transmitted towards the single UE. The maximum number of simultaneous data transmission in the downlink is 8 layers. But at the UE side, maximum is that is capable is the 4 unit. 4 antenna is there. So maximum layer that is possible in the downlink due to towards the single user, that is the 4 layers. That is the maximum layer is less than equal to minimum of node B capability, comma UE receive capability. The receive capability is less. That's why this is the targeting factor, right? The maximum layer that is the possible towards one UE, that is the 4 layer. That is the downlink single user MIMO. If you have any question in between, then please ask us. And one main concept towards the multi-user MIMO. Single user MIMO, I have discussed that is the point-to-point MIMO and multi-user MIMO. That basic concept is the pairing. What it means pairing? The selection of the multiple UEs for multi-user MIMO is called the pairing. How the two UE are specially separated so that the orthogonality between the two radio channels may be achieved. That selection of two different UE that is specially separated is called the pairing, multi-user MIMO pairing. And what is the advantage of this pairing? It allows the special multiplexing of the what is special multiplexing? Same frequency time domain resource allocation to different UE at the same time. Same time and frequency allocation to different UE. Same radio resource can be allocated to different users. That is the specially separated. That is the multi-user MIMO concept. Pairing concept. Here you can see here, left and right, the special multiplexing for there are two channels in the physical channel, two channels in the downlink. First one is the PDSCH and second one is the PDCCH. PDSCH, that means physical downlink shared channels that is allocated for the user's data, and PDCCH, that is the allocation of control data. And for the user data, their resource allocation in terms of resource block and resource RB and RBG, resource block group. And in case of PDCCH, the resource allocation in terms of resource element group and REG and CCE, control channel element resources. Actually, these are the grouping of the resource element. All of you know the resource element. The resource element grouping in the case of PDCCH allocation, that is the CCE. In case of the user data allocation, that is the RB resource block and RBG. Here in left hand side, you can see here the currently in the PDSCH supports up to 16 layers for special multiplexing. What it means? It means if the 16 UE are paired, 16 UE are paired in the spatial domain, they can serve with the same time frequency domain resources. Or we can say same, they are allocated to same resource block group. That is the advantage of special multiplexing for PDSCH in the downlink as a multi-user MIMO. And multi-user MIMO only supported in the NR-TDD, or we can say C band, or in the millimeter wave band. In the right hand side, special multiplexing for control channels, or we can say PDCCH, right? The maximum layers that is supported in this for control channel, that is the 4 layers. The 4 layers PDCCH, what are the advantage of this? Control channels are specially allocated same frequency and time domain resource. It increases the PDCCH capacity and also the control channel element utilization and save the CCE resource. Right. This one is the concept in the multi-user MIMO in the downlink direction, and same uplink multi-antenna reception concept is there. The procedures for the uplink multi-antenna reception, you can, there are 3 steps. First step is the G node B. I have already told you the UE actually send the sounding reference signals to estimate the channels, right? And accordingly, G node B allocate the resources in the form of DCI, downlink control information to the UE and notifying the UE for the optimal rank and PMI. What is the PMI? That is the pre-coding matrix indicator. Rank means what is the number of layers that is useful to the users. And after assigning the resource by G node B, the UE actually uses the optimal PMI value and decode the PUSCH data and transmit it. UE transmit the data and then G node B decode the PUSCH data. These are the procedure in the uplink direction, how the uplink multi-antenna reception take place. And uplink single user MIMO, that is capability is the single user can support simultaneous transmission of up to 4 layers in the uplink direction. In this figure, only uplink 2 layers is shown here, but maximum that is 4 layers is feasible in the uplink direction. That is the single user MIMO.
Sir, this single user MIMO, if the UE supports more than 4 simultaneous communication,
right?
so is it that all the UE which are available have got only 4 antennas only?
Actually, if UE supports more than 4 layers, you want to say, na?
Yeah, yeah.
It is not feasible actually. It is not feasible till now because our wireless channels, our propagation channels will not be orthogonal in that case, because our antenna at the user side, they are very close to each other.
Okay.
That's why the correlation between the path or wireless channels is very high. So you cannot achieve more data rate.
Okay.
It is not. It is not. It is not good for the implementing more than 4x4 MIMO in the uplink direction.
Okay.
So uplink multi-user MIMO, that is the different channels you can see here. The physical uplink shared channel. For user data transmission, there are 2 types of physical channels. In the downlink, that is the physical downlink shared channel. For uplink, that is the physical uplink shared channel, PUSCH. It supports maximum 8 layers for the spatial multiplexing. 8 layers for spatial multiplexing means you can see here the same radio time and frequency domain resource is allocated to different 8 UEs. That is paired. G node B only allocate the same radio and time domain frequency and time domain resources to different UE only when they are paired. Paired means they are G node B check whether they are specially separated or not. then they allocate the same frequency time domain resource to all the 8 UEs. So maximum supporting level for uplink multi-user MIMO, that is the 8 layers. Currently, in future maybe more than 8, but currently it is a 8 layers for special multiplex. Now single user and multi-user MIMO, if you have any question regarding single user, multi-user MIMO or FTD, TDD, why we are using the time division duplex in the massive MIMO, not FDD, then you can ask. Then we will move for quiz, 2-3 sample quiz.
In uplink multi-user, 8
Yes,
UEs
yes.
can be paired, while in downlink 16 UEs can be paired. Why there is a difference in uplink and downlink pairing capacity?
Why there is a difference between uplink and downlink?
Yes.
Because of capability, na? Because of capability in the downlink, na? In the downlink, you can install more number of antenna elements so that the beam forming, na? We will discuss after a few slides, na? Beam forming concept. Their beams are narrower in the case of downlink direction because they have more number of antenna. But in the case of uplink, the more number of antenna in comparison to the base station is not feasible to install at the smaller unit, that is the user equipment.
Sir, as you said, in case of multi-user uplink, downlink,
Yes,
the orthogonality is maintained because the same frequency in the same time domain resources can be
because
allocated.
orthogonality is maintained because of specialty. Users are separated in the space domain.
Okay. Sir, this orthogonality is managed by G node B.
Managed by G node B.
Okay. Okay. This is what my question.
Okay.
So
if large number of customers UEs are at one place, then orthogonality will be lost.
Their orthogonality will be lost, and the G node will decide which UE to be allocated the different same radio and frequency time domain resource. Orthogonality lost, but they cannot allocate the same time domain frequency resource. They can allocate the different time domain resource to different UE at the located at the same location, you can say.
And sir,
The
if
different
during the please sir.
suppose 16 layers is there, such maximum 16 layers is there in the downlink, and all the users are located at one place. The same frequency and time domain resource cannot be allocated to each users. They have to be different time domain frequency allocated by all the 16 layers to 16 users.
And sir, if during the conversation or communication, if
Right.
spatially apart users come together, then the other set of the orthogonal frequency will be used. Is it that way, sir? Initially we were apart, and
Initially we were apart. Okay.
and if in communication and during the communication we come close to each other.
Right.
So in that case, the other orthogonal
Actually,
frequency.
scheduling algorithm is time slot basis. G node B is resource scheduling, is scheduling is on the time slot basis. Time slot means after in numerology 0, it is the time slot is 1 millisecond. In numerology 1 means time slot is the 0.5 millisecond. That means G node B decide what are the radio resource allocated to users after every time slot basis.
Okay.
Radio resource allocation is done by every time slot basis, not one time resource allocated and it is going on always same time frequency resource allocated every time. But
Okay.
they are deciding factor after every time slot.
Okay.
And that time slot is varying depending on the subcarrier spacing, or we can say numerology.
Okay. Thank you, sir.
Okay, then we move towards the some small quiz. Which of the following is the main advantage of using massive MIMO over traditional MIMO? Options are diversity gain, 3D beamforming gain, single channel array gain, and multiplexing gain. Which one is more important? Actually, we can get all these four things from in the MIMO, but in the massive MIMO, what is the main advantage?
That may be single channel array gain.
Single channel array gain means you are adding single channel means your wireless channel in the one in the one domain na your horizontal and vertical rows na there is a box of antenna that means one single channel array. We'll show you na different box where the dipoles are cross polar dipoles are arranged in the horizontal and vertical plane. Single channel means for one antenna panel, single antenna panel.
So how do we calculate antenna beam width for the this MIMO antennas?
How do you calculate?
Yeah.
Actually, G node be calculated depending on the pre-coding matrix. I have already shown in the first slide, na? The SRS base weights of antenna, and we will discuss in detail na, after some slides.
Okay, thank you.
Give the answer.
D multiplexing gain, I think.
The massive MIMO, that is the 3D beamforming gain.
So it's 3D
3D
beamforming gain.
beamforming gain.
3D beamforming gain is the correct answer. Multiplexing gain is also true, but it is the main. It is not the overcome from the 3D beamforming gain. Main advantage is the 3D beamforming gain. Second question is the which of the following is the key technology to enhance the high altitude coverage in the 5G network? Please mute yourself. It is generating the noise actually. Uplink and downlink decoupling. Actually, a downlink is missing here in this question. Uplink and downlink decoupling, and filtered OFDMA and 256 QAM and massive MIMO. Which one is the key technology behind the high altitude coverage?
ठीक है मैं बात करूँगा क्या पड़ जाएगा
Correct answer is the massive MIMO. Correct answer is the massive MIMO.
Last question, can you show again?
Your mic is mute. Sandeep sir.
Kindly unmute your voice. Sandeep ji, please unmute your
Voice is not coming. So your voice is not coming. Sandeep ji.
Sandeep ji, may I request you please unmute your mic.
संदीप जी आपका वॉइस नहीं आ रहा है.
Okay, now sir, audible?
Yes sir, yes sir.
Okay. Sorry, actually automatically we have on the this question.
Yes, quiz 3, yes. Question 3.
Question 2 is correct, na? Massive MIMO.
Massive MIMO.
Question
Yes.
3 is.
Sir, answer for question 2 is massive MIMO, but it is because of beam forming only.
All right, beamforming only. We will discuss how massive MIMO use as a 3D beamforming after subsequent slides. Then only
So
we cover the elevated building, na?
So reduce intra-cell interference.
Yeah, it can reduce the intracell interference.
So that's why is it answer enhance cell coverage?
In that case, question number 3, enhance the cell coverage by increasing the array gain, by improving the array gain.
B is the right answer.
Actually, in question number 3, na, which of the following benefits cannot be achieved by massive MIMO? Actually, massive MIMO is used as a multi-user MIMO, na? Where the complexity of the user equipment is not enhanced, na?
Your voice has gone again. संदीप जी आपका वॉइस ब्रेक हो गया.
Now okay?
Yeah, now
I think this would connect with the.
बढ़िया. आज किसकी तरफ से? अच्छा, हमारी तरफ से चला के.
Now okay, sir? Am I audible?
Yes, sir. Yes, sir. Yes, sir.
Okay.
Yes, sir.
So the answer of the third question is the improved single user peak rate. It cannot be achieved by massive MIMO. And fifth question is the massive MIMO is most suitable in which transmission mode?
TDD, sir.
TDD.
TDD is the correct answer. TDD is the correct answer.
The fourth is remaining, sir.
Fourth is okay. Actually, number you don't check the number, na? Fourth question comes in subsequent slide, some other slide actually, after some other slides. Okay. Now, after the massive MIMO, the beamforming overview, how the beamforming implemented in the 5G. That is the basics. If we add two antenna, two dipole antenna, add in the phase signals and amplitude in such a way that their power is enhanced in the desired direction. Enhanced is improved in the desired direction, or we can say in the desired UE direction. Am I audible to all now?
Yes,
sir. Yes, sir.
Okay. That means if you are adding more and more number of antenna elements, or we can say dipole antenna elements, our antenna gain will be more and more. If you add more and more antenna elements in our panel, that means antenna panel, that means the gain of the antenna is becomes more and more. And beam width of the antenna will be lesser and lesser. That is the concept of beamforming. Am I audible to all or
Yes.
Some disturbance is there from. Am I audible?
Yes,
Yes,
sir.
sir, audible, but some
Okay.
background disturbance is there.
Okay, okay, sir. The beam forming. What is the beam forming actually? The main concept behind the beam forming is the antenna weight calculation of the antenna weight actually. What is the antenna weight? We will discuss. The with the beam forming actually, G node B weight the signals to form a narrow beam towards the target UV. In one line, if you want to say beam forming, what is the beam forming? Beam forming is the G node B weight the signals in such a way to form a narrow beam towards the target UV. To form a narrow beam towards the target UV. Am I audible to all of you now? Actually, some I think data
Yes,
issue
sir.
is there.
Yeah, yeah, it's okay.
Yes,
That's why.
yes.
You can go ahead. It's okay.
Right, sir. With the beam forming, basically, G node B weights the signal in such a way that to form the narrow beam towards the target UV. As a result, coverage performance is improved and UV are more accurately targeted. Interference SNR is also improved, right? So how we can achieve this waving of the signals antenna, all of these we will discuss. This slide shows the full dimension MIMO. Also, it is known as the 3D beamforming. 3D beamforming where your beams are moving in the azimuth direction as well as in the elevated direction in the building, top floor, 10th floor, 20th floor, right? This is the beamforming features actually. It is, and the beamforming, with the help of beamforming, your beams are narrower and narrower. What it improves? It improves the SINR. It improves the signal to interference noise ratio. And after improving the SINR, your throughput will be increased. Right? If SINR is increased, that means your throughput will also increase. And another case is the spatial separation or multi-user MIMO. In the case of multi-user MIMO, capacity as well as throughput both are increased. Capacity means total cell capacity of the users. Because same time frequency domains you are using to different users that are specially separated in the space domain. Na? In the right hand side is spatial multiplexing. Same thing is written here. That is 4 layers. Your G node B are transmitted towards the UE. In that case, only throughput will be increased. That is the normal MIMO or point-to-point MIMO. So massive MIMO improves the capacity and spectrum efficiency as well. Capacity in terms of multi-user MIMO and efficiency because they are using the same frequency time domain resource to different users. Now beamforming approaches. Approaches means what are the types of beamforming, right? What are the type of beamforming? You can see here the analog beamforming, digital beamforming and hybrid beamforming. We will discuss detail 1 to 2 slide of all these things. Analog beamforming means antenna weights adjusted in analog signal, or we can say analog domain. What is the antenna weight actually? Whenever we use the antenna weights or weight something like that, it is termed as a phase and amplitude adjustment to the signal that is allocated to an antenna element. Antenna weights means phase and amplitude of the signal. Right? In the analog case, That is, the antenna weights are adjusted in the analog domain, or you can say RF domain. And in the case of digital beamforming, that antenna weights are adjusted in the baseband domain or digital domain. And hybrid is a combination of both analog as well as digital. In the 4G, only digital beamforming is used, where special layers, 4 layers and maximum 8x8 layers are possible in the downlink direction. That is because of digital beamforming. But in 5G, they are using both analog as well as digital. That means hybrid beamforming. The preferred approach for 5G is a hybrid beamforming. This one is a slide showing that the analog beamforming, where the phase and amplitude of the antenna elements are adjusted in the RF domain in such a way that the beams can be moved or steered in the as well as azimuth direction and elevated directions. Right? So analog beamforming, what it impacts actually? It impacts the radiation pattern and gain of the antenna array, that it improves the coverage, and also it also overcome the path loss created in the millimeter wave spectrum.
Sir,
And digital beam, yes, please.
Sir, this analog beam forming, the isotopic radiation from each one of the antenna element is visible to all the element, but only thing is that at some location of user it is getting constructively interfered. Am I right, sir, in my understanding?
Omnidirectional antenna means?
Sir,
what do you want to say?
Suppose one antenna element of in the MIMO, if I see its isotropic radiation, that will be visible to all the devices in the region. But only thing is that the beam is getting constructively interfered at the user's location. Am I right in my understanding, sir?
It may constructively interfere with at the user side, but for that there are different measurement report is there by which they are adjusting their modulation, their coding rate, all of these, or they narrower the beam also. The beam width is not fixed in the case of 5G. Beam width is also varying depending on the interference, depending on the distance that the travels the users are away from the base stations.
So, sir, when we conduct the EMR test on the like say 5G BTS, we have to ensure that no beamforming mechanism is on. Otherwise, at the point of testing location,
actually EMR radiation is not going to measure the only one beam. Actually, they are measuring the overall radiation, not single beam. Even in that scenario, in the current scenario, 4G, 3G, 2G, EMR actually measuring the all the radiation that is coming from base station or which coming from any other interference. Okay, they doesn't know what are the beams are coming from, where base stations are there. Okay, they doesn't know anything. They only measures the power density, right? They are measuring only the EMR meter is only measuring the power density.
Sir, agreed. This is the broad. You are telling about the broadband. If you are going to frequency selective, then we can find out the power for the each frequency band also separately.
Right, sir. Right. So, 20 resource block for that, sir. Because we will discuss what are the frequency that is allocated to one beam.
Yes, sir.
Right, sir.
Okay, sir.
And then the digital beamforming. Digital beamforming already used in the 4G, right? What are the advantage of analog beamforming? There is the RF chain you can see in this image, there are multiple antenna in the RF domain, but there is a RF chain, means digital to analog converter and power amplifier, everything are a single RF chain. But in case of digital beamforming, it is also sometimes known as the pre-coding or baseband beamforming. In that baseband pre-coding, a number of RF chain is there. Your data is layered, or you can say transmitted on that RF chains. That is the baseband pre-coding, baseband beamforming. Different beams are transmitted on the different layers in the digital domain. Right, sir? This is digital domain beamforming, and where the number of channels, the multiple RF chains is there in that case, digital beamforming. The pre-coding, you can see here in this picture, what we get in reality. Actually, this is one is the just block transmitter and receiver, where they are propagating everywhere. If one antenna is transmitting everywhere, that means receiver 1, receiver 2, receiver 3, and transmitter 2 is also transmit everywhere at the receiver 1, 2, 3. That reality is like this, and what we want, the independent propagation path. Orthogonal path we want for decoding the data, actual data, increasing the throughput. How can we get? By this one is the mathematical form. Actually, the matrix is there, same above for this. So how we will achieve? By adding the pre-coding matrix in the digital domain. That is the beamforming. This one is the important, how the beamforming we got in the radio environment. This is the 4-step beamforming procedure. After that, after beamforming procedure, we will some slides for the how the beamforming application in the initial SS domain, and after the latching the cell. The first last one, that is the beamforming procedure. That is the channel. 4-step is there in the beamforming procedure. That is the first one is the channel calibration. Second one is the weight calculation. Weight is always, I have said that the phase and amplitude of the signals that is adjusted to the antenna input, right? Then waving, how they calculate, and then how then weight is implemented, and then beamforming, how they adjusting their width and direction of the beam. Right, these are the 4 steps. First is the channel calibration. Right, the NR TDD uses the same frequency in the uplink and downlink. The strict channel reciprocity between the uplink and downlink channel is required. For that, to achieve the reciprocity, to achieve the strict reciprocity, we have to calibrate the channels by sending the some reference signal, SRS, CSIRS. By channel estimation, they can adjust their channel reciprocity also to achieve channel reciprocity. The second step is the weight calculation. What is the weight calculation? What are the weights that is implemented to the antenna so that the beams are going towards the user's equipment? There are 2 methods actually. The accuracy of weight calculation in the downlink channel based on the 2 methods. First one is the SRS weight, and second one is the pre-coding matrix indicator weight. The SRS weight is applied to the cell center users, and PMI weights applied to the cell edge users. And these are the adaptable, not only SRS or not only PMI. Right. And the left hand side, you can say SRS is the sounding reference signal that is transmitted in the uplink. And the G node, we calculate first the calibrate the channel, and then calculate the weights. what are the antenna weights required, right? And then send the weights toward the UE to implement that weight in the uplink direction as well as in the downlink direction. The similarly, second method is for the CSIRS weight. CSIRS is a downlink reference signal used for the channel estimation. The both the CSIRS and SRS reference signal used for waving purpose to calculate the weight of the antenna that is implement to the input of the input of the antenna. And this adjustment selection of the SRS and CSIRS is used depending upon the uplink. You can see SRS pre-SINR, the threshold level. There is a threshold level. You can see here the if you want to change from SRS to PMI base or from PMI to SRS base, there is a threshold 2 dB and 8 dB are configured in the G node B, so that they automatically adjust as whether it is SRS based calculate the weight or PMI CSIRS based weight they are calculating. So all these are weight calculation is done by the G node, whether it is SRS or CSIRS. These weight calculation is actually important to implementing the beamform. This one example how the weights are added in the RF domain. You can see here the number of layers there are. Number of layers are there. How many layers? There are 8 layers in the there. All the 8 layers are actually weight are adjusted in the all the TRX. Suppose this is example of 64 T 64R. 64 TRX is there, and all the input signals that is weighted to adjusted all the input, all the layer. You can see here na total number of layers is 8. All the 8 layers are implemented in all the 64 antenna. All the 64 antenna. All the 8 layers are going to all of these 64 antenna, not only one antenna. But how they achieve the beam? Because of their weight of the antenna signals. Weight of the antenna signal, depending on the beams are steered. Right? So beam forming, there are 2 types of beam, that is the dynamic beam and static beam. That we have already discussed, SRS based and PMI or CSIRS based weighting is called a dynamic beam. Dynamic beam means their beam width, their gain, their direction are not fixed. But in the 5G broadcast channels, our control channel and broadcast channel uses the predefined weight value to generate the discrete beam, which is called the static beam. Right? For, or we can say for data channel, for our traffic channels, they are using the dynamic beam, and for control channels, for broadcast channels, they are using static beams. For static beams, that means the predefined weight values are there to generate the broadcast beam. But for the user data, yes sir.
Sir, this control channel,
Yes.
where this will be pointing towards, whether it is for all the coverage area of that antenna, or like say there has to be some directional gain in that also, or it is a broadcasting in all direction.
Our coverage is actually coverage is defined by the SSB block, or we can say broadcast channel. Right, the coverage is coverage is by the broadcast beam. Right, broadcast beam is there. The coverage is defined that man. That broadcast beam is the analog beamform.
Okay.
Right one. The broadcast beam just is a analog beam forming. The within the broadcast, I will discuss in the subsequent slide. Our data beams are more than more thinner organs. You can say more thinner beam width of the data beam, but it is a wider beam. Our static beam is a wider beam. Our broadcast beam is a wider beam, that is the analog beam forming.
Okay.
And it is a predefined weight.
Okay.
Right, sir?
Okay, sir.
Okay. Now the some initial SS procedure and beam forming operation. First, SSB, might be all of you knowing the what is the SSB. The SSB is the synchronization signal block that is used for the coverage verification in the 5G network. That's why it is known as the beacon sweeps through the beam. It is a predefined weight actually. SSB transmit in the predefined weight in the fixed direction. Right. The first find the frequency, then the this is the acquisition, how they acquire the UE is acquire the network. Then this synchronize downlink synchronization with what primary and secondary synchronization signal from the SSB block. After synchronization, they read the information from the broadcast channel. And also in the broadcast channel, there is a system information block 1. In the MIB, there is a location information of the SIB1. And after that, they read the SIB1 and apply the cell selection criteria and the latch with the cell. Up to this stage, it is only downlink synchronization. Now they are approaching for the uplink synchronization. Up to this 4th step, now the UE is synchronized in the downlink direction and latch with the cell and select a PLMN. What is PLMN code? Anyone tell me what is the PLMN? How they select the PLMN? By reading the system information block 1. The PLMN is the used also in the 3G, 2G, na? MCC plus MNC, mobile country code and mobile network code. That is
public land mobile network.
Yeah, public land mobile network. That is one code is there that is transmitted in the SIB1. That is the MCC plus MNC. And after cell selection, they synchronize in the uplink. That is the contention batch ratch procedure. Contention batch, and tomorrow we will discuss the what is the different approaches of random access procedure. Okay. And that synchronization purpose, there is a RAT procedure is there for uplink synchronization, and then they establish the RRC connection between the UE and G node B. Right. And the 2 slide where we are showing the new radio initial SS procedure for the assay networking. I think all of you know now the what is the assay standalone mode 5G. How they actually acquire. Previous slide is na. This slide is showing the block direction, and this one is the UE searches the SSB and complete the downlink direction. This one 4 step, find the frequency, downlink synchronization, and read the system information and cell selection. You can say here na, downlink synchronization, obtain the PCI. What is the PCI? All of you know PCI, physical cell identity. What is this? And demodulate the MIB.
G node B. That is G node ID, physical ID.
G node B ID, very good. G node B, this is the identification code for the G node B base station. 4G and 5G. 5G is also using the same identification code and 4G same, but their range is different. And the range of PCI in the 5G is from 0 to 1007. Right. So PCI is the identification code of G node B. 4G also using the same identification code. In 3G, it is uses the scrambling code, primary scrambling code as an identification code of the base station. And GSM, they're using the base station identification, BSIC, BASIC. They are using the BASIC to identify the base station. The first one is the first block is showing the downlink synchronization. Then second block is showing the they read the SIB1 message and camping on the cell. And after third one is the RAG procedure. And after completing the RAG procedure, they synchronize. They complete the RRC connection and complete the initial SS procedure. This one is the NR initial procedure. How they their signaling connect with the UE with the core network. Right. This is the non-standalone deployment option. There's a few difference in the NSA and SA. And in the tomorrow session, in the SA call flow and NSA call flow, we will discuss in detail the how the UE complete the attachment in the LT, then activate the E node B to add the G node B as a secondary node, right? And then they UE the complete the random access procedure with the 5G node.
Yes,
in the NSA, there is already all the EPS bearer and radio bearer and SRB, DRB are already present. After adding the G node B, they starts uplink synchronization by using the random access procedure. Okay, so we will discuss in detail in tomorrow class. Now this slide is important. I have taken from the award solution. And you can see here the in LT there is a coverage is a one sector, one beam. One sector, one beam. You can see here in this, na? This one is the less than 3 gigahertz, and this one is the C band, and this one is the millimeter wave band. So less than 3 gigahertz, less than 3 gigahertz band means they are using only 4 synchronization signal block. Within a one sector, there are 4, you can say within a one cell, there are 4 subcells for verifying the coverage. Now in the 5G, your coverage is not the cell based, it is a SSB based, or you can say subcell based. Yeah, or you can say beam based coverage is in the 5G. In the less than 3 gigahertz spectrum, or you can say they are less than 3 gigahertz supports both 5G and R supports both FDD and TDD. But this scenario, C band and millimeter wave spectrum band, they are supporting only TDD and RTDD. So maximum number of possible SSB blocks in less than 3 gigahertz spectrum is 4, whereas in the C band that is the 8, maximum 1 to 8, and for millimeter wave spectrum total number of beam sweeping that is the 64. 4, 8 and 64. This one is the how the beams actually move. This beam actually with the calculate with the predefined weight. This is the analog beam forming. This SSB beam actually it is a analog beam forming, or we can say predefined weight. Static beam, we can say static beam or analog beam, or they are applying the predefined weights. Predefined G node we apply the predefined weight so that it transmit in the specific direction with the specific width, beam width. Okay, within a 5 millisecond, it is a burst period. You can say burst period is also known as the group of SSB block. Group of SSB block less than 3 gigahertz. That is the 4 group of SSB blocks. In the case of C band, it is a 8. In the group, there is a 8 SSB block. In the millimeter wave, it is a 64 SSB block is there. And these SSB bursts are repeating after every 20 milliseconds. Okay, in this slide, you can visualize the SSB block, how the SSB block is arranged in the frequency and time domain resource. First one is the primary synchronization signal. And a pink one is the broadcast channel, and this light green color is the secondary synchronization signal. The frequency domain resource for physical broadcast channel is the 20 resource block. And for primary synchronization signal is the 12 resource block, and secondary synchronization signal, it is also 12 resource block. That means total in SSB block is a total in the frequency domain is the 20 resource block. And in the time domain, it is a 4 symbol. The 4 symbol. This is the structure of the SSB block that is transmitting, that verifies the coverage in the 5G network. That is using the predefined weight to form the beam,
Sir, how do you we notify the G node B about change of location in case of a moving vehicle or any moving object?
Actually, there are measurement report always. They are UE are sending the measurement report, periodical measurement report to the base station.
Okay.
Right. That's why they measuring. Suppose one of the parameters is the RSRP, received signal reference power, received reference signal receive power. Sorry, reference signal receive power. That indicate the loss. Actually, how the path loss is there. If you move away from the base station, your path loss is more and more. So that's why they are calculating each and everything. Is there are different reference signals that are transmitted by the base station. By reporting the UE, they know the users are moving and their channel is are varying very fast. Accordingly, they allocate the resource to the users.
Okay.
Okay, sir.
Okay, thank you.
So same, the initial SS, I have previously in the slide and the blocks, you can see here the different synchronization signal block. The 5G uses the SSB beams for coverage purpose. Different within a sector, there are 4 beam in the case of less than 3 GHz spectrum. If 5G uses the less than 3 GHz spectrum, 8 SSB beam possible if they are using the C band, and 64 SSB beam possible if they are using the, or you can say G node be configured with the millimeter wave spectrum. And these are the steps. The read the SIB1 and reference signal, and then transmit the PRAS for uplink synchronization. How they are latched, actually latch with the G node B, how the UE latch with the G node B. And this beam forming is not only in the downlink direction. Beamforming is in the both in the 5G UE as well as G node, both they are using the beamforming downlink as well as in the uplink direction. Now this picture is very important, where you can see here there are different SSB beam. I have already told you the SSB beam is verify the coverage in the 5G. Within SSB beam, it is a wider beam. It is an analog beam forming. It is a predefined weight that is applied on the antenna element. Within that SSB1 beam, there are many CSIRS beam. You can see here, na? CSIRS beam, what it means? It means it is a digital beam. Your user data is going in the CSIRS beam. That is the digital beam. This one is the CSIRS1, CSIRS2, CSIRS3. These are the digital beam forming that is used for the user data. This one is the control channel. SSB1 is the control channel, that is the predefined weight, and CSIRS beams are the beams that weights beam forming of the weight is defined by the which weight, as SRS based weight or CSIRS weight. Yes, sir. The CSIRS beam is also traffic, and it is a narrower beams, and SSB beams are the coverage and wide beams. So how they are tracking the beam, na? from in the idle mode from SSB2 to SSB1. Beam tracking is based on the CSI report. We are discussing about different reference signal. Na? These are the different signals, or we can say pilot channels that is used. Actually, CSIRS only used when UE is connected. The CIRS is the UE specific reference signal. CIRS is a UE specific reference signal, but our PSS and secondary triple S secondary synchronization signal and broadcast channel, these are the which types of signal? That is the not a UE specific, that is the cell specific. The beam tracking is based on the CSI report configured. So what the G node be transmit the CSIR reference signal and the UE actually calculate, and some of the estimation they just send the report on the PUCCH or PUSCH. These are the two physical channel in the uplinks. They may send sometimes PUCCH or sometimes PUSCH. And what the information they send, the beam number they are sending the CSIRS RSRP. They are sending the SSB index of the RSRP. Not only this CSIRS RSRP, but also the signal strength of this SSB index. And decision to the change the beam is based on the reported RSRP by the UE. From 6, from 3 to 2 or 2 to 1, they select that beam or track the beam. Right. I think this one is the last slide. After that, we have some quiz. The scenario based.
Sir, before
please.
Sir, before we go to the other slide, sir, I still want to ask the first question which I have asked, sir. Suppose I am going for a EMR radiation test of a 5G BTS.
Right.
So I am standing in front of the antenna. So there will be two beams. One will be the kind of a control channel which you say SRS, right?
Right.
And sir, it is quite likely the data channel beams are pointed towards the sky, where I can never reach and measure the actual amount of emission observed at that point. So
why you are correlate with the EMR tester? EMR tester
sir,
is
why I am asking is, sir, why I am asking is the very purpose of the EMR testing is that there should not be at any point in the network, anywhere in the network, the radiation should not exceed certain amount of predefined level.
But
so,
sir,
Sir, it is at up to street level.
Radiation
For
radiation purpose, na different power density radiated by different frequency band that is given by the TEC, I think, or any term cell that is providing for different band. Na? Actually, in the for 2G, 3G, and 4G also, they are all transmitting in the sub 3 gigahertz band. So their calculation of the power density is different, and if you apply this in the millimeter wave spectrum, their frequency, the calculation of the power radiation is different.
Okay, sir, I agree. What you say.
I have not read the document of the millimeter wave spectrum radiation pattern, how the power density will be calculated in that case.
Sir, I agree whatever you say up till now. My only question is that if I am standing in front of an antenna and if I am able to read my control channel, but the traffic channel power may be pointed in some other direction other than the point where I am standing. So the radiation of that directed beam, let's say towards the sky, is not, I am not able to measure, and that is the actual radiation which is going to be exposed to by the users. So that is what
I understand your question. You want to say your SSB beam somewhere else and your CSIRS beam data beams are somewhere else.
Yes, this is what
you want to say. Similar type of thing, na?
Yes, sir.
But they also track the beam of SSB beam or coverage beam. If some measurement report is required, na, So
Yes,
some
sir.
signaling is suppose during the data transmission, some signaling is required to send on the that SSB block. Okay, they are actually SSB broadcast channels. Informations are repeated after every 80 millisecond. How they read the broadcast information? If they are not, they are far away. Suppose broadcast beam are in some other direction and your user data beam in some other direction. So they also track the same beam. The wider beam, the broadcast beam is a wider beam.
Okay, sir.
There should be same, na? In the same SSB block, there is a within the same coverage. They have the thinner beam, or you can say refined beam in the case of data beam. So they are the different scenario on the basis of the operators. They provide 5G provide the horizontal coverage of users like that in the first slides, and also they provide the high-rise building coverage by using the beam forming in the elevated direction, right? And
Yes.
This one is the business district where the both horizontal and vertical users are present there. Then 3D beam forming can be used here. And
Yeah.
also there is a one scenario-based use cases application, that is the inter-cell interference scenario. The beam, they are interfering with other users. They can increase or decrease or change the direction of beam so that they cannot interfere with each other. So these are the some applications. Actually, there are many more applications or scenario-based application, but I have found from the Huawei white paper this applications. I think it is good, so I have added in my slide. Right. If you have any question, then please ask me. Otherwise, then we will go to the quiz. 6, 7, actually.
Sir, EMF, regarding the EMF up to below 3 gigahertz, the formula was F by.
Actually, I don't know regarding
No,
the.
I'm telling you, sir. Actually, the TEC is preparing, still TEC is preparing the 5G EMF test procedure. That is not still finalized.
Actually, up to 3 gigahertz, they are already specified.
Yes.
What is the power density?
Yes.
Again, beyond that 3 gigahertz, they are not specified actually.
The
For C band and millimeter.
ICNRP guidelines set the frequency by 200, and our DOT has specified F by 2000. The minimum frequency range in a megahertz will be divided by 2000, then you will get the power. That is the limit.
That is for less than 3 gigahertz spectrum, na? Not
yes.
for C band or millimeter wave band.
Yes. So still
I have not read any document regarding C band and millimeter wave band that is specified by DOT. Na? ICNRP is
DOT
good.
is still working
that is
on it, sir. TEC is still working for finalization test procedure for the high frequency band for 5G.
Okay.
TEC is still working on it.
TC is working on it. Okay, right,
yes.
Sir.
Right. Thank you.
Thank you, sir. Thank you, sir. Any other questions from your side?
I think you have explained very nicely. Thanks for the very nice presentation. It was very informative and quite clear.
Thanks, sir. Thanks, sir. Now some 2 or 3 quizzes there that is also uploaded in that assignment. The how many layers are supported by PDSCH for special multiplexing for 5G? PDCH is what? Uplink channel or downlink channel? It is a downlink channel. That's the physical downlink shared channel. What is the number of special multiplexing defined in 5G? Initial version of 5G, you can say.
16.
16. 16 is the correct answer. And antenna weight calculation. That is, antenna weight is very important in the case of beam forming, na? Whether it is analog beam forming or digital beam forming for SSB block or data block or CSIRS beam. That is the antenna weight calculation for the downlink characteristic by which method? SRS weight, CSIRS weight, both, none.
Both.
Both is the correct answer. Right, both is the correct answer. And last question is the which types of beam used by the SSB in 5G? Static, dynamic, both, none.
Dynamic.
Both.
No, sir, I have already told you, na. The SSB beam is the control channel beam, na. It is a static beam. It uses the predefined weights. Actually, SSB beams are transmitted, not all the beams at the same time. They are all the SSB index not transmitted at the different time in the different direction. That's why there is no interference within a cell, or we can say between the SSB index. So SSB beam is the static beam currently, at least. Okay, sir. That thank you. And summary, we have studied today the principles of massive MIMO and some wireless basic. Then massive MIMO, TDD mode. There we are using massive MIMO in TDD mode and single user MIMO, multi-user MIMO. Beamforming basic and how the procedures of beamforming, and then initial access procedure. We have all actually discussed today in this session. Then thank you to all. If you have any question, then please ask.
Thank you, Mr. Sandeep Singh. It was a very nice and detailed presentation you had given with respect to MIMO, the process of beamforming, and detailed inputs about the beamforming. So it would give a better insight of all these topics to all those who are participating in this session. So thank you once again. Thank you on behalf of NTI-PRIT and all the who are participating in this session. Thank you.
Thank you, Atul sir. Thank you.
Thank you, Sandeep.
So we should.
Thank you, Sandeep. It's a good presentation, and I thank from all the participants to you. Thanks a lot.
Thank you, Satyaji. Thank you.
अतुल जी एक ब्रेक मिलेगा क्या 10-15 मिनट?
Pardon, sir?
ब्रेक होगा क्या? कंटिन्यूस क्लास चलेगा?
ठीक है. Okay. So 5 minutes or 10 minutes break?
Yeah, 10 minutes will be sufficient.
Okay.
Thank you.